Somewhere inside a lab, cooled to a temperature colder than the empty void of deep space, sits a machine that can explore more possibilities in a single second than there are atoms in the entire observable universe. It doesn't work like your laptop. It doesn't even work like the world's fastest supercomputer. It works by bending the strangest, most counterintuitive rules of physics ever discovered. Rules that even Albert Einstein himself once found deeply unsettling. This is a quantum computer, and understanding how it actually works means understanding something genuinely bizarre about the nature of reality itself. By the end of this video, you'll actually understand what a qubit is, why physicists keep talking about something called superposition as if it explains everything, and why an entirely separate phenomenon called entanglement had Einstein himself uncomfortable enough to argue against his own field's conclusions for years. More. Importantly, you'll understand exactly why building a machine based on these principles turned out to be one of the hardest engineering challenges humanity has ever attempted, and exactly what these strange machines can and cannot actually do once you strip away all the science fiction hype surrounding them. Let's start with the computer sitting in your pocket or on your desk right now, because understanding what makes quantum computers different requires understanding exactly what came before them. Every classical computer, from the earliest room-sized machines built in the 1940s to the smartphone in your hand today, runs on the exact same fundamental building block, something called a bit. A bit can hold exactly one of two values at any given moment, a 0 or a 1. Every photo you've ever taken, every song you've ever streamed, every word of every document you've ever typed, all of it eventually breaks down into unimaginably long strings of these simple zeros and ones, flipped on and off billions of times per second by tiny electrical switches called transistors. Think about just how much has been built on top of that one simple foundation. A single bit doesn't seem like much on its own, just an on or off switch. But string together 8 of them, and you get a byte capable of representing any number from 0 to 255, or any single letter, punctuation mark, or basic symbol your keyboard can produce, string together. Millions or billions of these bytes, organized through increasingly sophisticated layers of software. And you eventually get everything from a simple text message to a full-length streaming movie to the complex financial systems tracking trillions of dollars moving around the global economy every single day. The entire modern digital world, every website, every app, every video game, ultimately reduces down to unfathomably long sequences of these same simple zeros and ones. That system has worked remarkably well for the better part of a century. Modern processors pack billions of transistors onto chips smaller than your fingernail, performing calculations at speeds that would have sounded like pure science fiction just a few decades ago. But there's a specific category of problem that this entire approach, no matter how fast or how many transistors you cram onto a single chip, simply cannot handle efficiently. Problems where the number of possible solutions doesn't grow steadily as the problem gets bigger, but instead explodes exponentially, doubling and doubling again with every small increase in complexity, until the total number of possibilities dwarfs anything even the most powerful classical supercomputer could ever hope to check one at a time. Imagine trying to find the fastest possible delivery route, connecting just 30 different cities. That sounds like a modest, almost trivial-sized problem on the surface, but the actual number of possible routes connecting 30 cities is larger than the total number of atoms in our entire galaxy. A classical computer solving this kind of problem has to essentially check possibilities one after another, or use clever shortcuts to rule out large groups of bad options at once, but it's still fundamentally working through one path, one calculation, one step at a time, however fast those individual steps happen to be. Phi-S is exactly the kind of problem where quantum computers promise something genuinely revolutionary, not just fast or ordinary. Computation, but an entirely different mathematical approach to exploring possibilities in parallel all at once. Here's where things start getting genuinely strange, in the best possible sense. Instead of an ordinary bit that holds either a 0 or a 1, quantum computers use something called a qubit, short for quantum bit. And a qubit can exist in what physicists call a superposition, a state where it's simultaneously exploring both 0 and 1 at the exact same time, not flickering rapidly back and forth between the two values, but genuinely occupying some proportional blend of both possibilities simultaneously, right up until the precise moment someone actually measures it. That idea alone breaks most people's everyday intuition about how the physical world is supposed to work, and for good reason. In our everyday classical experience, a coin sitting on a table is either heads or tails, full stop, whether or not you've bothered to look at it yet. But a qubit genuinely isn't behaving like a hidden coin whose result was already secretly determined the moment it landed, with the actual answer just waiting patiently for someone to check. According to quantum mechanics, the qubit is genuinely undetermined, existing in a real mathematical mixture of both possibilities, until the specific act of measurement itself forces it to collapse into one definite value or the other. Now here's where superposition transforms from an interesting physics curiosity into genuine computational power. If one qubit can represent a blend of two possible states simultaneously, then two qubits linked together can represent a blend of four possible states all at once, 0, 0, 0, 1, 1, 0, and 1, 1, existing together in superposition simultaneously rather than one at a time. Add a third qubit, and you're now representing 8 possible states simultaneously. This growth isn't gradual or additive. It's exponential, doubling with every single qubit you add to the system. A quantum computer built from just 50 qubits can theoretically represent more simultaneous possible states than there are stars in the observable universe, all existing together in superposition at once inside a machine that could physically fit on a modest-sized table. Encryption key at a time, a sufficiently powerful quantum computer can, in a very real mathematical sense, explore an enormous number of different possibilities simultaneously, all within the same quantum state, all at the same time. But superposition alone doesn't fully explain how quantum computers actually extract a useful answer out of all those simultaneously explored possibilities. And this is where a second deeply strange quantum phenomenon enters the picture, something called entanglement. When two or more qubits become entangled with each other, their individual states become correlated in a way that has no equivalent anywhere in ordinary classical physics. Measuring one entangled qubit instantly tells you something definite about the state of its entangled partner, even if that partner qubit happens to be sitting on the opposite side of the same chip, or at least in carefully controlled laboratory experiments, even physically separated by significant distances entirely. Einstein himself famously found this specific phenomenon so deeply unsettling that he dismissively referred to it as spooky action at a distance, refusing for years to fully accept that nature could genuinely behave this way. Decades of increasingly rigorous experiments since then have confirmed entanglement is absolutely real, a genuine, measurable feature of how our physical universe actually operates, at the smallest scales, not some kind of measurement error or theoretical curiosity waiting to be explained away. Quantum computers deliberately engineer and carefully maintain entanglement between their qubits, specifically because it allows information to be processed collectively across the entire system, rather than qubit by qubit in isolation, creating rich, complex correlations that classical bits simply have no way of replicating. So how does a quantum computer actually turn superposition and entanglement into a genuinely useful calculation, rather than simply an impressive-sounding physics demonstration? The process generally works something like this. Researchers first prepare a set of qubits into a specific, deliberately engineered superposition, essentially setting up the mathematical starting conditions for whatever problem they're trying to solve. Then, they apply a carefully choreographed sequence of operations called quantum gates, precisely timed pulses of laser light, microwave radiation, or other tightly controlled physical signals, depending on exactly what type of hardware the specific quantum computer happens to use. These gates manipulate the relationships and interference patterns between all the qubits' superimposed states, gradually amplifying the mathematical paths that lead toward the correct answer to the specific problem, while simultaneously causing the countless incorrect, unhelpful paths to cancel each other out through a phenomenon called quantum interference, similar in spirit to how overlapping ripples in a pond can either reinforce each other or cancel each other out depending on their timing. That interference concept is genuinely the secret ingredient that separates a real quantum algorithm from simply having a lot of qubits sitting around in superposition doing nothing useful. Superposition by itself just gives you access to a huge number of simultaneous possibilities. It doesn't automatically tell you which of those possibilities is actually correct. Quantum algorithms have to be extremely carefully designed using precise mathematical sequences of quantum gates, specifically so that when you eventually measure the system, the wrong answers have mostly canceled each other out through destructive interference, while the correct answer has been reinforced through constructive interference, making it dramatically more likely to be the specific result you actually observe when you finally take that measurement. Designing algorithms that pull off this delicate mathematical trick for a genuinely useful real-world problem turns out to be remarkably difficult, which is exactly why only a relatively small number of genuinely useful quantum algorithms have actually been discovered since the field began, despite decades of dedicated research from brilliant mathematicians and physicists around the world. Finally, after this whole carefully orchestrated sequence completes, researchers measure the qubits, and that measurement is precisely the moment superposition collapses into a definite, readable classical answer, a specific string of ordinary zeros and ones that a normal computer can then interpret and display. The entire elegant, complicated dance of superposition and entanglement exists purely to make sure that final measurement, that one definite readable answer, has an unusually high probability of being the genuinely correct solution to whatever exponentially difficult problem the researchers originally set out to solve. Building an actual physical machine capable of doing all of this reliably turns out to be extraordinarily, almost absurdly difficult. And this is exactly why practical, genuinely useful quantum computers have taken so many decades longer to develop than early. Enthusiasts initially predicted back when quantum computing was first theorized in the 1980s. Qubits are almost unbelievably fragile. The tiniest disturbance, a stray vibration passing through the building, a fluctuation in ambient temperature, even a single cosmic ray passing harmlessly through from deep space can instantly disrupt a qubit's delicate quantum state, a process physicists call decoherence, essentially destroying the very superposition the entire calculation depends on before it ever finishes. That's precisely why quantum computers require such extreme, almost theatrical operating conditions to function at all. Many current quantum computers, including some of the most advanced machines built by companies like Google and IBM, use qubits made from superconducting electrical circuits that only exhibit their necessary quantum properties when cooled to temperatures colder than the depths of outer space, hovering just a fraction of a degree above absolute zero, the theoretical coldest possible temperature in the entire universe. Other approaches use individual trapped atoms or ions, precisely suspended and controlled using intricately focused laser beams, requiring similarly exacting, almost surgical levels of environmental control to keep the delicate quantum states intact, long enough to actually complete a useful calculation. Even under these extraordinarily controlled conditions, errors still creep in constantly, and dealing with those errors has represented one of the single biggest technical obstacles standing between quantum computing's enormous theoretical promise and any kind of genuinely practical, everyday usefulness. Unlike classical computers, which can simply copy a bit multiple times and compare the copies to catch and fix mistakes, quantum mechanics contains a fundamental rule called the no-cloning theorem that makes it physically impossible to perfectly copy an unknown qubit's exact quantum state without destroying the very information you're trying to preserve in the process. Researchers eventually solved this problem through an elegant, considerably more complicated workaround, spreading a single unit of protected quantum information across many physical qubits simultaneously, arranged in careful, mathematically precise patterns that let the group of qubits collectively detect and correct errors without ever needing to directly measure and thereby destroy the fragile information itself. For nearly 3 decades after this error correction concept was first theoretically proposed back in 1995, researchers struggled mightily to actually demonstrate it working the way theory predicted it should. Every time scientists tried building larger versions of these protective error correcting patterns, the overall error rate stubbornly got worse rather than better, the exact opposite of what was needed for quantum computers to ever scale up into something genuinely useful for real-world problems. That finally changed in December of 2024 when researchers at Google demonstrated for the very first time a quantum chip where adding more physical qubits to the protective pattern actually made the resulting system exponentially more reliable rather than less, finally crossing what physicists call the error correction threshold, a milestone the field had been chasing for 30 consecutive years. So what can these increasingly capable machines actually accomplish right now in the real world beyond impressive sounding? Physics demonstrations confined to laboratory settings? Quantum computers show especially strong promise for simulating other quantum systems directly, an area where classical computers are famously and fundamentally inefficient, since accurately modeling how individual atoms and molecule S interact with each other requires tracking an enormous, exponentially exploding number of quantum interactions simultaneously. That specific capability could eventually accelerate the discovery of entirely new medications by allowing researchers to accurately simulate exactly how a candidate drug molecule will interact with a specific protein inside the human body, long before anyone needs to synthesize and physically test that molecule in an actual laboratory. It could similarly help researchers design dramatically more efficient batteries, better performing solar panels, and entirely new categories of industrial materials, all by accurately modeling their fundamental atomic behavior in ways no classical computer can practically match. Quantum computers also show genuine promise for solving complex optimization problems, exactly like that 30-city delivery route example from earlier, with real-world applications ranging from optimizing complicated global shipping and logistics networks to managing electricity flow more efficiently across enormous, interconnected power grids. And in a considerably more sobering, widely discussed application, sufficiently powerful quantum computers could theoretically break several of the mathematical encryption methods currently protecting almost all of our online banking, private communications, and digital security infrastructure, which is exactly why governments and major technology companies around the world are currently racing with real urgency to develop new quantum-resistant encryption methods before any adversary manages to build a machine actually capable of breaking the older systems first. It's genuinely important to understand what quantum computers are not, though, since popular science fiction and breathless media coverage have created some significant, persistent misconceptions worth directly correcting. Quantum computers are not simply faster versions of your laptop, capable of effortlessly speeding up every single computing task you might throw at them. For the vast majority of everyday computing tasks, checking email, browsing the web, editing a document, streaming a video, classical computers remain considerably faster, dramatically cheaper, and far more practical than any quantum machine current TLI in existence or likely to exist any time in the near future. Quantum computers only offer a genuine, meaningful advantage for that specific, narrower category of exponentially difficult problems we discussed earlier, ones involving simulating quantum systems directly, breaking specific types of mathematical encryption, or solving certain highly complex optimization challenges. Outside that specific category of problems, an ordinary classical computer remains not just adequate, but genuinely superior in essentially every practical sense. If you find topics like this fascinating, the ones that take a genuinely strange, seemingly impossible sounding scientific concept and actually explain how it works underneath the surface, go ahead and like this video and subscribe for more. This channel exists specifically to break down exactly these kinds of complex frontier scientific topics into something genuinely understandable, without oversimplifying away the fascinating, counterintuitive details that make the underlying science so genuinely remarkable in the first place. Because here's the actual takeaway worth holding on to once the specific technical details about qubits, superposition, and entanglement eventually start to blur together in memory. Quantum computers aren't Magi-C, and they aren't simply faster versions of the ordinary computers already sitting in your home or your pocket. They represent an entirely different, genuinely strange way of processing information, one that exploits the deepest, most counterintuitive rules governing our physical universe, rules that took the greatest scientific minds of the 20th century decades to even begin to properly understand. We're still in the relatively early chapters of learning how to reliably build, control, and meaningfully use these strange machines at any kind of practical scale. But the fundamental science underlying them, superposition, entanglement, and the careful, elegant choreography of quantum interference, represents one of the most genuinely mind-bending intersections of pure physics and practical computer engineering that human beings have ever managed to seriously attempt. If you find topics like this fascinating, the ones that take a genuinely strange, seemingly impossible sounding scientific concept and actually explain how it works underneath the surface, go ahead and like this video and subscribe for more. This channel exists specifically to break down exactly these kinds of complex frontier scientific topics into something genuinely understandable without oversimplifying away the fascinating, counterintuitive details that make the underlying science so genuinely remarkable in the first place. Stranger way of processing information, one that exploits the deepest, most counterintuitive rules governing our physical universe, rules that took the greatest scientific minds of the 20th century decades to even begin to properly understand. We're still in the relatively early chapters of learning how to reliably build, control, and meaningfully use these strange machines at any kind of practical scale. But the fundamental science underlying them, superposition, entanglement, and the careful, elegant choreography of quantum interference, represents one of the most genuinely mind-bending intersections of pure physics and practical computer engineering that human beings have ever managed to seriously attempt.